Okay, it's a great pleasure to introduce Romina Arroyo from the Universidad de Córdoba and CONICET, speaking on the signature of the Ricci curvature on nilmanifolds.
Okay, thank you very much, Caroline, for the introduction. And thank you so much, the three of you, Caroline, Ramiro, and Emilio, for giving me the opportunity to speak in this great seminar. I am so happy for that. So today I'm going to speak about this, about the signature of the Ricci curvatures on nilmanifolds. This is a joint work with Ramiro Lafuente. You can find the article on arXiv. And well, Ramiro Lafuente is working at the University of Queensland. Okay, so as always, I like to start with the problem. So this is the problem in which we are interested with Ramiro. So we want to determine this set. So if you have a nilpotent Lie group G, and you have a left-invariant metric on G, so you can compute the Ricci curvature, and also you can compute the signature of its Ricci curvature, okay? So now if you have another left-invariant metric, you can do the same, okay? So varying left-invariant metrics on a fixed nilpotent Lie group, you will have a set of signatures, okay? So the idea is try to understand or try to determine or describe completely this set. So the set of the signatures of the Ricci curvature varying left-invariant metrics on nilpotent Lie groups. Okay, so I would like to say a few things about the problem in the setting of Lie groups. So of course, you can study this problem, which is a classical problem with no homogeneity assumptions, but we are interested on homogeneity spaces, so that is the reason we decided to study the problem on left-invariant metrics on Lie groups. And in this setting, so we have different cases. For instance, you can study the problem on semi-simple Lie groups. And when you study the problem on semi-simple Lie groups, well, there is so there are only two semi-simple Lie groups in which we know these sets. We completely know the sets. So these are SL2R and also SU2. So this is a well-known fact from this paper of Milnor. But then when you look at Lie groups in higher dimensions, for instance, you can ask the same question and try to determine the set on SL2C. But then in that six-dimensional real Lie group, so it is unknown if there exists some left-invariant metric in which the Ricci the Ricci curvature is negative. Okay, so in dimension 6, it's an open question. And also, when you look at the problem on the other side, so in solvable Lie groups, so we have this article of Jorge Lauret and Cynthia Will, in which they give an overview about Lie groups admitting negative Ricci curvatures. And there you can see that the problem of determining whether this point is in the set that we are interested for solvable Lie groups could be out of reach. So this is the reason why we decided to study with Ramiro the problem on nilpotent Lie groups. So this is a kind of justification of why we decided to study the problem and try to understand completely the answer of our problem. So in nilpotent Lie groups, there are no negative Ricci curvatures. So we do not have this problem. Okay, so this is the problem. And now I would like to review briefly some definitions about nilpotent Lie algebras, just in case you don't know them. So first of all, is if you have a Lie algebra, so you can consider this series, okay? When you have a nilpotent Lie group, a nilpotent Lie group is a nilpotent Lie algebra is an algebra in which this series at some point stops. So there exists some natural number J in which one of these ideals is equal to 0. And if the previous ideal is different to 0, so then the Lie algebra is called J-step nilpotent. So here I miss one J. There. Okay. Examples. So if you want to have some one example in mind, for instance, if you consider strictly upper triangular matrices with this bracket, so these are nilpotent Lie algebras, and just in order to give you an example, this is the Heisenberg Lie algebra. So this Lie algebra has dimension 3, and it is two-step nilpotent, just in order to give an example. Okay. So now, we are working on nilpotent Lie groups with left-invariant metrics. So we call the nilpotent Lie group capital N and the left-invariant metric G. And when you have these Riemannian manifolds, so these Riemannian manifolds are determined at the Lie algebra level. So you have a nilpotent Lie algebra, and also if you take the Riemannian metric in the identity, you have an inner product. So here, the nilpotent Lie algebra, so the bracket in the Lie algebra, we will call by mu. So this is a bilinear form which satisfies Jacobi, and it is skew symmetric. So from now on, we will work at the Lie algebra level most of the time. So if you have this data, so this is the Ricci curvature. The Ricci curvature. So this is a formula, well-known formula. So if X is an element on the Lie algebra and you take an orthonormal basis Xi, so this is the Ricci curvature. So here, of course, all the information that you need to know is the inner product and also the bracket mu. So what I mean with the set of signatures of the Ricci curvature, well, here is written in terms of the inner product. So you have S minus will denote or will represent the maximal dimension of a subspace in which the bilinear form is negative. The same for S plus, and we will consider these triples of integer numbers, and the set in which we are interested is this one. So we will vary all inner products on our Lie algebra, fixed Lie algebra, and then we will compute the Ricci curvature and the signatures. So what is known about these sets? Okay. So first of all, I am gonna start telling you some facts in low dimensions, and then I'm going to say some things about arbitrary dimensions, and I am going to come back to these low dimensions results. For instance, in dimension 3, in this paper of Milnor, the signature of this Heisenberg Lie algebra, so there exists only one nilpotent Lie algebra, which is known the abelian Lie algebra, and it is the Heisenberg Lie algebra. And if you take any left-invariant metric on or any inner product on H3, so the signature will be always the same. Okay? So the set is only one point, and the point is this one. So what happened in dimension 4? Well, in this article, they studied these sets, and so here we have only two nilpotent Lie algebras. One of them is the direct sum of H3 with R, and there we only have 1 point, again, in our set. And the other nilpotent Lie algebra of dimension 4 is this filiform Lie algebra. That means this 3-step nilpotent Lie algebra written in a basis. It has this form. And here the set is more interesting because here we have 3 different points, so 3 different signatures. Okay, and in this example, I wanted to say a little bit more, so how we can get these signatures in order to give some examples. And for instance, of course, so we have a Lie algebra. We can take the inner product in which this basis is orthonormal. Okay, so you will get a signature there. And then, in order to prove this inclusion, so we can vary the inner products taking diagonal matrices. Okay, so if we look at what happened with the signatures of the Ricci curvatures of this matrix, so you will have that you can get these 3 points. Okay, these 3 points. And in the following slide, I am gonna show you why we have the other inclusion. This is dimension 4, and then there are results in dimension 5 given in these articles in dimension 5 and in dimension 6, and as far as I know, there are no results, non-results in dimension 7. So one of the question is why there are no results in dimension 7, and until dimension 6, so these sets are computed case by case. Okay, so from dimension 7, so we know that in dimension 7 there are families of nilpotent Lie algebra, so maybe it could be hard to compute these sets because we have infinity many nilpotent Lie algebras, and in dimension 7 the good fact is that in dimension 7 there is a classification, but then if you think of the problem in higher dimensions, there is no classification because, of course, the classification of nilpotent Lie algebras and dimensional nilpotent Lie algebras is not well understood, so the problem is getting harder. So these are the facts in low dimensions. What is known about arbitrary dimensions? And here, so there is this article from Milnor in which he proved that S minus and S plus has to be at least 1. Okay, at least 1. And then in this other article. So we have that S minus has to be at least 2. That is the reason why. So here we only have 1 point. And here we have these 3 points. Why? Because I like to see the Ricci curvature like this. So we need to have at least 2 minus, okay? And at least 1 plus, okay? So the question is, can we get there can we get there a minus, a 0, or a plus? And the answer is that bearing these diagonal matrices on the inner product, so you can get the 3 possibilities. There are also results about the 2-step nilpotent Lie algebras. So here DVW is the same article about the results in dimension 6. And so here they prove that if you have a 2-step nilpotent Lie algebra, so the set is only 1 point. Okay, and you will have this number. Oh no. So you will have this number of minus, this number of positive, and this number of zeros. So in 2-step nilpotent, the set is well understood. And also in this article, these mathematicians study what happened with some Lie algebras admitting nice bases. Okay, so this is our main theorem with Ramiro. So I am gonna try to speak as much as I can, because there are a lot of information in there. But what we prove in this theorem with Ramiro. So if you take any nilpotent Lie group, and you look at the set of signatures of the Ricci curvature, so that set has to be this one. And that set is described in terms of theoretical data, Lie theoretical data, okay? So here, this is the center of the Lie algebra N, so the elements of the Lie algebra which commutes with the entire Lie algebra. And then here we have the commutator. And then with the center and the commutator and the dimensions of them, we have these numbers. And as you can see, so these numbers are fixed and depend, all of them, of the Lie bracket. And with them, so we can say how it looks, or we can determine or completely describe the set of Ricci, the set of the signatures of the Ricci curvature bearing left-invariant metrics for any nilpotent Lie group. And from now on, I would like to focus in this corollary here. So here, if you have a nilpotent Lie group with Lie algebra N, in which the center of the nilpotent of the Lie algebra is in the commutator of N. So here, so the description of the set is friendly. Okay, so that is the reason I would like to focus in the corollary. And here, if you look at AN, okay, so the center is included in the commutator, so then the intersection of the center with the commutator is the center. So an has to be 0. Okay. Since an has to be 0, so here in our union, so we have 0. So there is no union. And if there is no union, there is no R in our statement. Okay, there is no R. So then the corollary looks like is written there. And observe that set n here is the dimension of the center. So here is bounded by the dimension of the center. And well, un is the dimension of n minus the commutator. Okay, so from now on, I would like to explain the ideas behind of the proof of this corollary. Yeah, the ideas. Okay, is there any question?
Yes. So this condition in the corollary is equivalent to not having an abelian factor?
Yeah.
Ah,
yeah,
okay.
exactly. So if you, so any nilpotent Lie algebra, so in general, if you want to study the theorem A, so you can write, so you can write to your nilpotent Lie algebra as a sum of some central ideal A and another ideal N1, in which the Lie bracket is included in N1. So, and here you have part of the center, and here you have another part of the center of the Lie algebra. Yeah.
So the corollary is saying that all signatures are possible. I mean, yes,
Yes, I am going to explain that in.
all the obvious signatures are all possible.
Yes.
Okay.
That's right. That's right. Thank you, Jorge. Is there?
I have a question.
Yeah.
I'm not fully absorbing this definition of the set, but does it have kind of convexity properties that, I know we're working over integers, so you have to be careful, but does it disallow kind of jumps in dimension aside from jumping by 1 and going down by 1, or?
Yeah, there are some so in the nilpotent case, yeah, there are some connexity because so the Ricci curvature is a moment map. So and there you have some connexity properties. No? Does that answer your question? Convexity, I'm sorry, convexity properties.
I mean, is it, can you write it kind of as in terms of a convex whole of a set of triples, or?
Ah, okay. I understand the question. No, I don't think so.
Oh, yeah.
No.
Yeah, the union. Yeah, thanks.
Sorry.
In the corollary, I think you can, but in general, maybe you can, but we haven't been able to. The corollary seems like a simplex, right, of integers. Maybe I'm wrong.
I don't know. I don't know. So I can think and then write to you, Tracy. Okay, is there any other question? No?
Yeah. Can I just a small question? So I was at first surprised that it didn't seem that the step of your algebra mattered that much. It only mattered like the first derived ideal. but it seems that in the corollary, it looks like, for example, if you have well, no abelian factor and it's step 2, then it will work, right?
Yes.
Yeah. But so really, in general, there is no the step doesn't seem to matter. Just the first derived ideal, as far as I see, right?
No, I don't think so.
That's really cool. Okay.
Yeah, I don't think so. So if you have a two-step nilpotent, so I wrote that, but I don't think so.
Okay, thank you. It's just surprising. Thank you.
Okay, so now I would like to explain the proof or the ideas behind the proof of the corollary. And in order to do that, so I am going to start explain what is the approach that we use. And the approach is the following. So from now on, or in this slide, so we will fix an inner product on our Lie algebra M. Okay, and then we will consider this set B. Okay, so this set is all bilinear and skew symmetric form, okay, on N. And here in this set, so we have this action. So GLN acts on B and with this action. So this is this change of basis, this an action. And the good thing of this is that if you take a Lie bracket, if you take an element on B which satisfies Jacobi, that means a Lie bracket. So we have this. We have that these two Riemannian manifolds are isometric. So from one side, so we have this. We have this vector space M. So the vector space with this bracket, with this bracket, and this inner product, which is fixed. So this is the Riemannian manifold with this Lie bracket H mu and the left-invariant matrix determined by this inner product, which is fixed. And on the other hand, we have the vector space, this bracket, and we consider this inner product. Okay, so this is the Riemannian manifolds in which the Lie bracket is mu. So the bracket of the Lie algebra is mu, and the left-invariant metric is determined by this inner product. Okay, so these two Riemannian manifolds are isometric. So the idea here is that we want to understand what happened with the Ricci curvatures of all these all these inner products, so determined for all these inner products. So we will vary H in there, but it's the same to vary H in here. Okay, so the idea is to understand or to study what happened in this side, in the left side. Okay, why we like that? Because so in the left side, the inner product is fixed, and we are varying only Lie brackets. So there we can use results from Lie theory and also from geometric invariant theory that and that is the idea of the proof. Okay, so that is the reason that is the idea of the proof. Okay, so now I am gonna start with the proof of the corollary. So remember here the center is included in the commutator, and we would like to describe to prove this equality. So we will take one inner product okay? Any inner product, and we will prove that it satisfies that S minus is bounded by UN and S plus is bounded by Zn. So remember, this is the Ricci curvature. So we have the Ricci curvature, but look at the formula. So if you take one element X in the center of the Lie algebra, so the bracket of that element with XY is equal to 0. So see, X is in the center of the Lie algebra, so this is equal to 0. Okay, and if that part is equal to 0, so we do not have this part of the this part, so these are the terms will survive. Okay, but if the center is included in the commutator, so then this has to be positive, strictly positive. Okay, so this is telling us that if you take some element in the center, so the Ricci curvature is positive. That means the bilinear form on the center is positive definite. Okay, and what happens if you take some X in the orthogonal complement of the commutator? So this term will disappear. Okay, so if X is in the orthogonal complement of the commutator, that term will disappear. So here we will have something negative. Okay, so what I am saying here is that the Ricci curvature is positive definite in the center and is negative definite in the orthogonal complement of the commutator. So then at least S plus has to be the dimension of the center, okay, and that was Zn. And here S minus has to be at least the dimension of the complement of the commutator, which is UN. Okay, so we have one of the inclusions. So now we would like to prove the other inclusion, and in order to do that, we need to prove that for any of these triples, S minus, S not, S plus, satisfying this, there exists a Riemannian a left-invariant matrix with that signature. Okay. So here, that is if we want to prove. And now we are using this approach. I didn't say that, but this the approach of varying Lie brackets instead of inner products is an approach that Jorge Laroet used in many of his papers. So you can find this approach in his articles. And here we will fix an inner product. So we'll fix an inner product and we'll consider this decomposition. We'll consider this decomposition. So here, remember, so the center of N is included in the commutator. So here, if we take the orthogonal complement of the commutator and then we take an orthogonal complement of the center, so we have this decomposition. And the idea of this proof is try to use the geometric invariant theory, okay? And in order to do that, so we will consider some closed subgroups of GLN. In this case, we will consider this GM, this subgroup, and we could prove, so in the article you can see that we could prove that this orbit, so remember GLN acts on B by this change of basis. like this. If you consider this orbit, so this orbit is closed. And why this is important? Because now we can relate this fact with geometric invariant theorem. And here we want to use this link which tell us about the orbit closed and zeros of some moment map that I am going to explain now. And here we have the link. So here we have this one is the Ricci operator. So if you have a fixed inner product and you have the Ricci curvature, you can contract the Ricci curvature with the inner product, and you can have an endomorphism. So this is the endomorphism. And the link with geometric invariant theory is this one here, that you can see the Ricci curvature as the moment map of our action. So the action of GLN on B. Okay, so here this pi denotes the differentiation of this action. Okay, and the good thing of that is that we can use all properties that we know about the moment map. So what is the idea behind this? The proof is that if you have this closed orbit, this orbit which is closed, so you can prove that there exists some element H on this subgroup GM, in which this new bracket H mu has the maximum amount of zeros. So when you look at the signature, so remember the previous slides. So here, this was the dimension of the center. Okay, and there, so the amount of pluses was bounded by the dimension of the center, and in this case we have exactly the dimension of the center, and here this was bounded by the dimension of the orthogonal complement of the commutator. So here we have the large amount of zeros that we can have. That is the idea. So using this link between closed orbits and the moment map, so we can get a metric or a Lie bracket in which the signature of the Ricci curvature has the largest amount of zeros. That is the idea. And once I'm not sure if okay. So the largest number of zeros. So then, why this is nice? Because then the idea of the proof is try to study the signatures close to this mu bar. Okay, and try to understand what happened close to this this mu bar, and there using some using the implicit function theorem, we can see that we can get we can reach all the possible signatures very close to this mu bar. So this zero is in an open. I'm not sure if I am say too much, but so bearing a little bit about mu bar, we can get all the possible signatures, and well, that is the idea of the proof. And okay, I think I was too fast, but that's all. Thank you so much. So if you have any question, please.
Thank you for a very interesting talk. Are there any questions? Oops. I have a question. Is there any chance that there might be, actually, let me check the chat. Is that a question? Yeah, here's the question in the chat. Does it make sense to study the problem and try to solve it for certain families? That's actually what I was going to ask. Certain families of solvable Lie groups. So, for example, almost abelian.
Yes, of course. Yes, so the question makes sense in some families of solvable Lie groups. That's yes, but so the problem is this is that the answer is yes. So it makes sense. It could be hard because of this article that I mentioned at the beginning of Jorge and Cynthia, but it's possible.
Is there any hope of doing it like for maybe a one-dimensional extension of a nilpotent or something like that? Or
I'm sorry?
For maybe like a one-dimensional extension of a special type or anything like that?
Yes, of course. Yes, it makes sense to study and also to apply similar techniques because since we know we have the moment map in is possible. Try to extend.
Just a quick comment. I think the main difference with the solvable case is the non-unimodular case, right? Because then the Ricci formula changes and there's an extra term.
But there is an extra term.
Modular solvable case, it should be possible at least.
Yeah.
If you restrict to like the Ricci solitons, do you know whether you lose some of the signatures or anything?
I don't know.
I probably could figure this out, but is like filiform? Is that where M is everything?
Filiform?
Like is that
is when you are n-1 step nilpotent.
Right.
So when you
that's when M is largest, I guess.
Yeah.
Right. The center is one-dimensional, and so that's where you have the most play. So your corollary is that everything is possible.
Yeah.
Right.
It's a very optimistic result, right?
Yeah.
It's very nice. Are there other questions?
And what about non-Riemannian metrics? Let's say Lorentz or something like that.
I haven't thought about Lorentz. I don't know.
You can do most. I mean, all the algebraic theory is the same. Then comes the metric problem, right?
Mm-hmm.
I'm just wondering whether, for example, the moment maps and stuff like that, it still works in that setting. I don't know. I really don't know.
Jorge.
You know, there is some interest in studying these weird metrics for in the nilpotent world, right?
Yeah.
It's not really a question, more of a reflection.
Yeah, reflection. Yeah. We can think about it.
So
This-
anyway, thank you. It was
I think there are some results, like even by some people in the audience. Like I remember a paper by Conti and Rossi, looking at the Ricci curvature of pseudo-Riemannian left-invariant metrics on nilpotent Lie groups, and there is a moment map formulation for that for the Ricci as well.
okay.
So maybe one can extend this. I'm not sure about the implicit function theorem part though, because
That's true.
that could fail, but I'm not sure.
Is the hardest part of the proof getting mu bar, or is it getting all this?
Our hard part was the implicit function theorem. So the last part, because we find some mistake in our proof, and that was the hardest part. I don't know. What do you think, Ramiro? But so
Yeah, I think we know better GIT than analysis.
We know better GIT. Yeah, that is.
So the implicit function theorem, it should be like, it's an exercise just, but you have to set it up in the right way, and it took us a while.
Yeah, but I think that the problem was to the technicalities in the general case with the with that part of the implicit function theorem. That was the hardest part, in my opinion.
Are there other questions? Well, thank you again for a very nice talk.
Thank you. Thank you for the invitation.